And then I can share screen. And then I think we're ready for class. I made a mistake starting class in my other class on Tuesday. I forgot to share my screen for a minute or two, So let me know if I make a mistake like that, if I'm talking and you don't see what I'm talking about. Please speak up and let me know that I forgot something. But let's go ahead and start. This is where we left off the other day on Monday. And we were talking, I was trying to convince you that a multi-threaded process is a reasonable way to try to write a program, especially a program that has to kind of attend to multiple things at once. We were kind of comparing a single threaded server, which could only talk to one client at a time. And if it blocked, like if it was doing IO on behalf of that client, everything else would have to wait. Whereas a multi-threaded server, if one of the threads was serving a client and other clients came along, we could start talking to them. And I'm kind of talking about things that'll show up later, but if if one of those threads blocked, like if it did an IO operation that took a moment, maybe a fraction of a second, the other threads could keep serving their clients while that one thread was blocked. So the ability to attend to multiple sources of IO, and even if one of those sources blocks, if you have to wait, the other threads can keep running. That's a valuable reason to use threads, even if you're not just using them for computational speed up. I pointed this out before, but I want to sneak up on a new idea with this. We said context switching between threads. The OS has to know about all the threads, so every process may have multiple threads. If a CPU is idle and a thread is runnable in any process, the OS ought to be able to let it run on that CPU. Even if other threads in the same process have to wait on something. So this lets the CPU context switch between threads rather than processes. If it's switching between threads within the same process, then that is simplified a little bit. And I think maybe we talked about this on Monday. When you switch between one thread and another in the same process, you don't have to switch the memory bounds. As long as you're within the same process. The only thing you have to do is save the state of the CPU and then let another thread running. Let another thread resume running. Why does this matter? Well, if you're switching between threads within the same process, you don't really need to be in kernel mode. So that could make it more efficient to switch between threads within the same process. In fact, if you don't need to be in kernel mode, you could potentially do that in user mode. A process without help from the kernel could switch between threads, could let one thread run on the CPU, and then it could say, oh, all right, I'm going to let this other thread run on the CPU for a while, as long as it's within the same process. And this gives us a way of implementing threads that I'm going to say we haven't thought about before, at least I haven't talked about before. There are really two ways of making threads. And again, this depends on the idea of switching between two threads as long as they're within the same process. Doesn't really require help from the kernel. Again, I don't have to change the memory that I have access to. There are other things that we'll talk about later that you don't have to switch as long as you're within the same process. So really, I'm sneaking up on the idea of two different ways of implementing threads. The one that we've been talking about so far, I would describe as kernel level threads. This is where the OS knows about all the processes running on the system, and it knows about all the threads within the same process. Inside the OS, we have to have little data structure for every thread just so that the OS knows about all the threads. It knows what state they're in. And by that, I mean some of them may be blocked, some of them may be runnable, and it can independently execute each thread. And that model, again, we'd call that kernel level threads. Sometimes you'll hear each thread in that model described as a lightweight process. It's like a process, the OS knows about it, but starting a new thread within the same process, we already saw that. We already saw this. That's cheaper than starting a whole new process. And that's what I've described up till this point. I'm trying to introduce the idea of user level threads. It's possible that to implement threads within a process without help from the kernel, like I said before, as long as you're within the same process, switching between different threads in that process doesn't require help from the kernel. So you could do that within your process. You could have a little bit of code that within your process that kept up with all the threads. And when one thread had to wait for something, it could look inside your process and decide what other thread, if any, gets to run for a little while. So this would be like putting a little bit of the OS inside your process, or at least in the form, typically in the form of a library. You might have a library that lets you make multiple processes within your thread, I said that backward, make multiple threads within your process, and time slice the CPU without any help from the OS. So really, and honestly, we do have two models of threading. Backing up, we have kernel level threads where the kernel keeps up with all the processes and all the threads they have, and user level threads where we can do this within the process. We can kind of divide up the CPU time among multiple executable components within our process. Here's a picture. I think I've edited this picture, but I didn't originally make it. But this shows these two models. Over on the left, we've got user level threads where you might have these blue boxes. I'm going to point at them with my mouse down here. Pretend those are CPUs or CPU cores. A process, when it gets a chance to run on one of those cores, so when the OS says, I'm going to let you run for a little bit, it gets CPU time, and then within the process, unknown to the OS, some threading library or maybe even some code that you wrote can divide up that CPU time, and it can say, I'm going to let this thread run for a little while, and then before the OS has even taken away the CPU from me, I'll save the state of that thread, and as long as I'm not executing privileged instructions, I can let some other thread run for a while and then let some other thread run for a while. So the CPU time given to a process, within that process, we can subdivide that among multiple threads as long as we don't need to change things like memory bounds. And as long as we're within the same process, we don't have to do that. Versus, this picture over on the right shows kernel level threads. For kernel level threads, the OS knows about every thread in the process. If there are multiple threads in the process, they could potentially, multiple threads could run at the same time. And I'm trying to find where it shows that in my picture. Maybe this thread could run on this CPU, and this thread could run on this CPU or this CPU core at the same time. So if you got multiple cores, multiple kernel level threads could run at the same time. They could even run on different cores from one moment to the next. So this thread might run on this core for a little while. And then if the OS decided later, I'm gonna let someone else run, but this core was available, maybe this thread could run on this core. Why, and again, what we've talked about up till this point, I would describe as kernel level threads. I'm introducing this new idea that you could implement threads within the process without help from the kernel. And I started to say a moment ago, why would you want to do this? Why is this a good idea? Well, it could be a lot less expensive. With kernel level threads, every time you want to make a new thread, that's a system call. Every time you want to context switch between two threads, that requires help from the OS. And if you did this all in user space, then the overhead could be reduced. And making more threads wouldn't consume kernel resources. So if the OS has limits on the number of processes or the number of threads it can support, if you're making threads that the OS doesn't even know about, then it's not gonna have an effect on those bounds. It's not gonna limit the number of threads you can make. And I guess one detail, this is a lot less important now, but in the early days of multi-threading, not all OSs supported multiple threads in a process. So if you wanted to be able to have a thread that was doing one thing and another one that was doing something else, you might have to do that. You might have to worry about that yourself within the process. I've got here an example. I tried it right before class, and it worked, but not as well as I hoped. Sorry, I'm using two screens today, and one screen doesn't show what I'm switching between. All right, here we go. I've got a virtual machine here, and it's running on my laptop. But in this virtual machine, it supports both models of threads. So these are mostly the same programs we looked at the other day. You'll remember we looked at Lots-O-Threads, which that was a program that made 10,000 threads just to see how long it took. We can run that again. I'll go ahead and run time, Lots-O-Threads. And you can see this is a different machine than we used the other day. And you can see making 10,000 threads in this VM takes almost a second. I've got a program called Lots-O-User-Threads. I think it's posted. I'll show you the code for it. Lots-O-User-Threads. And this is what I've started talking about now. The idea that you could make a multi-threaded process even if the OS didn't know that you were making threads. You would just have to do that within your process. You'd have to worry about context switching between threads, and you'd have to worry about, well, if one thread can't do what it wanted to right now, I'll run another thread as long as the OS lets me run. This is using a library called GNU Portable Threads. It is a user space thread library, so it carves up CPU time between multiple threads in a process without the OS, without any help from the OS. It's a lot like POSIX threads. The names are a little bit shorter and a little bit different, but I think the idea is the same. I have to include this header pth.h to get portable threads, GNU portable threads. Before I make any threads, I have to call this pth init. But then the rest of this is a lot like what we looked at. 10,000 iterations. I'm going to make a thread. This is kind of like pthread create. It's for GNU portable threads. It's called pth spawn. It lets you make a new thread. Same here, you pass it a start routine. You say, here's what your thread's going to do. And if you look up here, the start routine I'm using, just like before, it returns immediately. So my threads don't really do anything. I just want to see how expensive it is to make them. And then if once I've successfully made a thread, I join with it. So that blocks whatever thread is running in main until that other thread finishes. And then I go around and make another thread as fast as I can, up to 10,000 threads. So the point here is to see how this compares to kernel level threads. POSIX threads, unless you ask for something special, you're getting kernel level threads, but this threading library makes user level threads. So let's time Lots-O-User threads, and hopefully it'll be faster. Good, it's not colossally faster, but every time we made a thread, we didn't really have to make a system call, so the overhead was lower. In fact, if you look at the time the OS spent on behalf of our process, it was a lot more with kernel level threads and a lot less with user level threads. And the time, I guess we saved about 1/3 of our execution time. So moving back to our slides. This is the example I talked about. And these are some of the advantages. I guess I didn't talk about portability, but if you are if you're using POSIX threads like pthread create, that is a POSIX call. And for the most part, that's going to work on a Unix-like machine, but it may not work on other OSs. Whereas if you get your threads from a user space library, you can have a version of that library for whatever system you're running on. So those threads could work across multiple platforms. Those are the advantages, and they're mostly in the form of reduced overhead. Disadvantages, I've kind of hinted at these already. I think there are two disadvantages of using using just user space threads. One is, if the OS doesn't know about the threads in your process, then it can't schedule them independently. If you let me back up to my picture, if a system has multiple cores, but the OS doesn't know about the threads you're implementing within your process, then it's not going to let you run on multiple cores at once. So you're effectively going to get the CPU time at best, the CPU time of one processor or one core, and then you can subdivide that among your threads. So potentially less compute power, especially on a modern system with multiple cores. And the other is if you're backing up, if you're just doing user space threads, and a thread makes a call that has to block, that the OS has to do something for, then the OS, thinking that you're just one process, not necessarily knowing about the multiple threads you're subdividing CPU time among, it is going to mark you as blocked. It's going to put you in the waiting state, and then you're going to sit there until your IO is done, even if inside your process you have multiple threads that could be doing useful work. Over here on kernel threads, if the OS knows about all your threads, even if one of them makes a blocking call, if it says I need to do some IO or I want to wait until this thing happens, if the OS knows about the other threads within your process, it can schedule them to run on a CPU, even if one of your threads is blocked. And that's what I'm trying to say here. Sorry, I think I've got a whole slide for that. Yes, here it is. The blocking behavior is the biggest disadvantage of user level threads. If the OS doesn't know about the threads within your process and one of them makes your process block, it's not going to even run your process until the blocking has finished, until whatever you asked the OS to do has finished executing. Questions before we move on? So as a programmer, you really have a choice between which kind of threads you might use. Kernel level threads have a lot of advantages, especially upon scheduling and blocking behavior, but they have more overhead. User level threads are cheaper. We don't even require a system call to make them, but they have some disadvantages in terms of blocking behavior. As a programmer, shouldn't we be able to choose? Shouldn't we even be able to combine these? And the answer is yes. You can develop a program that has a mix of both types of threading, and we've got some names for the different models you could use. If you just use user level threads, that is, the OS schedules your process to run, and then within your process, you subdivide the CPU time that you get among multiple threads. We call that the many-to-one model. That's what this picture shows. The OS lets your process run, and then within your process, you might give a little bit of time to one thread and then a little bit of time to the next thread without the OS even knowing that that's happening. And you could write the code for this yourself. It would be a little bit tricky, but typically you would use a library to do this for you. And that's what we just saw. There are a few example libraries for this. And here's the one we just saw, GNU Portable Threads. That's what our example was, showing how we can make threads. We can subdivide CPU time among multiple executable contexts without the OS even knowing about it. So the model of just using user level threads, we call the many-to-one model. You could go the other way. The so the idea of many-to-one just means within your process, you might have multiple threads, many of them, but they all map to one thread that the kernel knows about. The kernel lets your process execute, and while you're executing, you subdivide the CPU time. The one-to-one model, like I started to say, it's kind of the other way around. Every thread within a process has a kernel thread that is executing it. So I guess said differently, the kernel of the operating system knows about every thread in your process. It is independently scheduling all those threads. And even if one of them blocks, if one of them makes a blocking IO call, the others are still executable. There are multiple examples of technologies that let you do this. This one in the middle is the one that we're using, pthreads. It says under Linux, but really pthreads is a POSIX standard. So even if you were programming on a Unix system that was not Linux, you could still expect to have access to pthreads. So every thread you make, the kernel knows about. Every thread you make requires a system call, but the OS can independently schedule those threads, including letting them run concurrently on multiple CPUs. These two models are the ones that I would say we already knew about. You can do user level threads or kernel level threads, or you could mix them. The many-to-many model says you could have multiple threads within your process, and the kernel could know about multiple threads within your process. And within your process, probably with the help of a library, you could decide when one of your threads gets to execute, who gets that CPU time. Like the picture shows, maybe the kernel is treating your process as if it has 3 threads. When one of those threads gets a chance to run within your process, probably with the help of a library, you could decide which task or which of the threads you've made gets a chance to run next. This is a little more complicated, but there are libraries to help you out with that. We're not going to use any of these this semester, but I've listed a couple of them up here. So the many-to-many model says you could have some large number of threads within your process that are backed by a smaller number of kernel threads. And whenever one of those kernel threads lets your process run, you could decide who gets to make progress, which of the user level threads you've made gets a chance to execute. This model is fine, but in practice, sometimes some threads are more important than others. Within your process, each thread may be doing a different task, and some of those tasks may be more important, which is why we have our last model, the two-level model. It says, all right, you may have a large number of threads within your process that are that are being time shared among a smaller number of threads that the kernel knows about. But you may have some special threads that are so important that you don't want them to share CPU time with all the other threads in your process. So for those more important threads, you can tell the OS to dedicate a kernel thread to those. Whenever that thread is executable, the OS knows that it can execute, and the kernel level thread that is dedicated to it will get a chance to execute it. I'm hesitating here because I want to say, provided no other thread is executing. So these are the two levels. You got a bunch of threads that are all sharing CPU time among a limited number of kernel threads, and you've got typically some more important threads that are backed by their own kernel level threads. That would let you have some of the best of both models. Making new threads over here is cheaper because it doesn't necessarily require a system call. Making these threads is more expensive but they don't have to share CPU time with all the other threads. Those are different models. So I introduced the idea of user versus kernel level threads, and I tried to describe how you could realistically use this in an application. Thinking ahead for this semester, this is important to know. And some models of threading are user level versus kernel level. But for us, when we're writing a homework assignment or something like that, we're mostly going to be using kernel level threads. When you make a new thread in Java, that is typically going to be a thread that is known to the kernel and can be independently scheduled. Questions before we move on? All right, people are still there, so I'm assuming nobody has any questions. There are other models. So there I was kind of talking about how you can use threads within your application. And as a programmer, you can decide, well, is this a job? Are these jobs that should be shared among multiple user level threads versus should they have a dedicated kernel level thread? But there are other ways of doing this. And a thread pool is a common way of trying to compromise between different models. This is a trick that has been implemented in a lot of languages, and it's fairly common in use. And it kind of splits the distinction between what jobs do I have to do, what tasks need to be done, versus what threads are going to do those tasks. I got a picture at the bottom of my slide that tries to show how to think about this. For a thread pool, you'll normally have a queue of tasks. And these tasks might be things like interacting with a client or doing some kind of compute job. As new tasks arrive, you put them in the queue. But you don't necessarily make a new thread to do that task. Because like I said, making a new kernel level thread could be kind of expensive. So instead of making a new thread for every task, how about if you have a pool of threads of typically a fixed or bounded size? You could pick that size based on the number of CPUs or CPU cores you have. If you have 4 cores on your system, maybe it doesn't make sense to be creating 100 threads if they can't all execute concurrently. So you could have a fixed sized pool of threads, and the job of these threads could be to try to drain that queue of tasks. Like I tried to draw this in my picture. You can think of this as a thread trying to do a task, and then once it's done, it goes back and either waits for the next task, or if there's already a task, it goes ahead and starts executing it. So think of your pool of threads as when there are tasks available, they all kind of cooperate to each one of them grab the next task, do it, and then look for another task. If there are no tasks available, they all end up waiting on the next task to arrive. What's nice about this? Well, if I've got a fixed set of threads, I'm not making new threads all the time. I've got a fixed number of them, and they're just trying to execute tasks as they arrive. Another nice thing about this is it separates the concerns of how many threads should you have, which might depend on your system. Again, if you got a fixed number of cores, maybe you don't need a number of threads that's way more than your number of cores. Separates that concern from how many tasks there are. If you start getting tasks faster than the number of threads your system can run concurrently, some of those tasks may have to wait, but you're not paying to make a new thread every time a new task arrives. So this is a good idea, but we're not the first people to think about this idea. The idea of a thread pool is so common that it shows up in existing libraries, including in Java. If you look in Java, there is java.util.concurrent. I don't have the name of the package, or sorry, the name of the class, but executor service is a model of making a thread pool. There are a few different models in Java, and it does what we just talked about. It makes a separation between the jobs that have to be done and the threads that are going to do that job. And if you've got a lot of jobs coming in, this can be a more efficient way of managing them. I mostly talked about the bottom of this slide. The stuff up here at the top, that's kind of stuff we talked about on the previous slides. So a thread pool is one way of kind of simplifying, again, the ideas of how many threads do I need in my process versus how many jobs, how many tasks are those threads going to do. Little bit of a change in topic. Any questions before we move on?
So,
sure.
If, for example, my computer has 8 threads, does that mean only 8 user or kernel threads can run at a time, or are kernel threads the hardware threads?
You said 8 threads, but I think you mean 8 cores, right?
No, I have a 4-core processor, but it's 2 threads per core, I believe.
So that is a detail that we don't talk about in this class. It's in your book.
Okay.
But so you got a system that does hyper-threading, which is a trick. I think it's an Intel specific trick.
It's an Intel processor, so.
Yeah, so they decided that it's a good idea to, if you think about it, each core knows how to compute things, but if that core has a cache miss, so if it has to go out to main memory, that's going to take a little while. So while that is happening, why not let that core do something else? That's where hyperthreading came from. Each core can kind of keep up with 2 threads that it might be able to run. And if one of the cores has, I think it's called a memory stall, if it has a cache miss and it has to go out and go to main memory, then it can, for a moment, it can run a different thread. Your OS can support any number of threads, up to some reasonable limit. So even if you've only got 4 cores or via hyperthreading 8 cores, your OS can keep up with 1,000 threads. It just has to make them share that limited number of cores. So your OS...
So only the 4 or 8 could run at a time.
Yeah, your OS probably thinks it has 8 cores because that's kind of what the CPU is made to do, but they can't really all be running at the same time. 4 of them could be. So your OS is going, but your OS is still going to schedule it as if you had 8 cores. So it's going to try to keep all those cores, both the, I want to say real cores, but that's not really the right way to describe it. But it's going to think it has 8 cores. So it's going to try to load them up all with whatever is runnable. And if there's...
do you refer to those as kernel cores?
The distinction between user and kernel is not really about how many cores you have. It's about who gets to make the scheduling distinction. So if let's say, I'll try to quickly say this example. Let's say you had 8 CPU cores, whether they're via hyperthreading or not. You had 8 CPU cores, and you only had 1 process, but it had 1,000 threads in it. If those were kernel level threads, then up to 8 of those threads could get a chance to run all at the same time. If they were user level threads, that is, you were taking the time that the kernel gave you and you were kind of subdividing it secretly without the knowledge of the kernel, then the OS is going to let your process run on 1 core, and then you can subdivide that time. So you would not get as much with just user level threads. You would not get as much use of the CPU.
Thank you.
I don't know if I answered your question. I hope I got close.
No, you did. Thank you.
Any other questions before we move on? So I hesitated here because we're kind of talking about different models of threading. For us, this semester, it's mostly going to be kernel level threads, but it's important to know about these other models, including tricks like, or common ideas like a thread pool as a way of separating concerns. I hesitated because we're going to switch to a few different little topics. And these are mostly about how threading makes some things more complicated. When they first designed Unix. And when they first developed the POSIX standard for Unix, they weren't worried about multi-threading. Systems would support multiple processes, but we weren't thinking about multiple threads within a process. And that meant that some of the ideas we had got stressed. They didn't necessarily make sense when we started putting multiple threads in a process. And I wanted to talk a little bit about a few of those. So as OSs have developed and as we've added more features, understandably, that kind of strains existing features. An example would be the kill call. We didn't see this system call, but we did see signals. A signal handler lets you say to the OS, when this signal arrives, here's what I want you to run. Here's the fragment of code I want you to run. The kill system call is how you send signals. We ran the kill command before, and when we did, it just turned around and made this kill system call. So this is what the kill command does. Kill, even though its name suggests that you're trying to terminate another process, you can try to send any signal you want with this. You just have to say who gets the signal, the process ID, and what signal you want to send. And each signal has a unique integer. For a single-threaded process, this made perfect sense. You send a signal to a process, it goes and executes the signal handler and then returns to whatever it was doing. For a multi-threaded process, this is more complicated because who should execute the signal handler when a signal arrives? If you've got 10 threads in your process, should one of them do it? Should they all do it? I don't know if there's a right answer to this because it kind of depends on what the signal is. If the signal is SIGINT, which means kind of a request to terminate your process, maybe all of your threads need a chance to clean up whatever they were doing. So maybe a SIGINT should go to all threads. If it's a signal because of some error, like SIG FPE, that's floating point exception, that means you did something like divide by 0. Well, probably only the thread that did that should get that signal. Other things like SIG-IO, that's if you're doing asynchronous IO, if you're doing non-blocking calls, the OS can signal you when IO is available. Maybe you've got a particular thread that's responsible for that. So these top three are kind of showing why a multi-threaded process is not necessarily a good match for the signal mechanism available in Unix. What did Unix do to fix this? Well, they said, you can figure it out yourself. We'll give you a mechanism that lets you decide who should get each signal. On modern POSIX systems, threads can block individual signals, and that's maybe not ideal, but it does give you some control over who gets a signal. You can block a signal in one thread, and if you want only one thread to handle that, you can leave it blocked in every thread except that one. This gives you some way within your program of controlling who gets a signal. That's not our only concern. A lot of other mechanisms, we have to figure out what they mean in a multi-threaded environment. And I listed a couple at the bottom, like fork. When you call fork, it was simple when we only had to worry about one thread. If you're running in a process and you call fork, then you return from that fork call and a new process gets made and it returns from that fork call. But what if the caller has 10 threads? If it makes a child process, does that child also have 10 threads? Well, that's what they could have done, but it's not what they did. They decided, designing Unix or designing the POSIX standard, they decided when you call fork, the child gets created, but it has only one thread. Even if the parent had a bunch of threads, the child gets made with one thread. And just like we saw with single-threaded processes, that child gets a thread that returns from the fork call running in a copy of the parent's memory, but with a different return value. Same for exec. When you call exec, what if you're running in a process that has 10 threads and you say, oh, I want to run this new program? Does it also have 10 threads? And the answer is, at least on a Unix machine, no. When you call exec, you start running a new program and it gets one thread running at the start of main. Even if you had 10 threads, 9 of them are going to go away when you call exec. The point here is to show, as particularly in the area of threads, but in general, as OSs develop and they add new features, it often puts strain on existing OS features. Slightly new topic. Any questions before we move on? All right, thread cancellation is kind of like kill between processes. It's the idea that you may make a thread and then you may want to terminate it. Maybe you made that thread and you gave it a job to do something, and then maybe the user hits a button to stop doing that thing, in which case that thread's job isn't important anymore. So typically we need a mechanism to terminate threads from other threads in the same process. And there are really two ways to do this, at least two models for how you could do this: asynchronous cancellation and deferred cancellation. Asynchronous cancellation says you ought to be able to kill a thread no matter what it's doing, just like kill between processes. No matter what it's executing, if another thread in the same process decides we don't need that thread anymore, it ought to be able to terminate it. Versus deferred cancellation, where you can terminate a thread, but not at an arbitrary point. If you try to terminate a thread, it will terminate, but not in the middle of what it was doing. It'll terminate at what's called a cancellation point. At some point within the thread, and I'm kind of giving away the stuff at the bottom of the slide, but where it knows that it's done with whatever it was in the middle of doing. You can define these yourself. You could, when you try to terminate a thread, you could mark locations where that thread, or you could write code for locations where that thread checks maybe a flag to see if anyone else has asked it to terminate. Within the OS, it has already done some of this for you. So some system calls that a thread might make are marked as cancellation points, as a place where a thread might automatically get terminated. So again, asynchronous cancellation, a thread could get terminated at any point in its execution as soon as another thread tries to terminate it, versus deferred, where it'll only get terminated at particular locations. One of these is a terrible idea, and it's the first one. Asynchronous cancellation is generally a bad idea in a multi-threaded process. And I kind of hinted at this. If a thread could be terminated in the middle of whatever it's doing, well, all threads in a process share the same memory. So what if the thread you tried to terminate was in the middle of updating a data structure and it wasn't done? Maybe it was rearranging nodes in a linked list, but it hadn't finished rearranging the nodes. If you kill it right away, that linked list is probably broken, probably has pointers that don't make any sense. And all the other threads in the process are eventually going to pay for that. That is, when they go to look at that linked list, it's going to be broken. It's not going to be in a consistent state. Between processes, an asynchronous cancellation mechanism like kill makes sense, or at least it could make sense, because when you kill a process, it goes away and all of its memory goes away. So there are no other processes that are going to be affected by its being terminated asynchronously. But between threads in the same process, asynchronous cancellation seems like a bad idea, because again, if that thread was in the middle of doing something important and I kill it, then whatever it was doing is half done, and all the other threads are going to suffer because of that. Java has a mechanism, or at least they had a mechanism for asynchronous cancellation. There's a dot stop method on a thread that'll kill the thread kind of no matter what it was doing. And in the early days of Java, this seemed like a nice mechanism to have. But if you try it now, it's marked as deprecated. This is how things are in Java. As features get added, we can't necessarily take them away, but we can mark them as no longer a good idea or no longer the right way to do that. So Java has a mechanism for this. It's just, if you compile a program that uses it, you'll see that that's no longer the right way to do a thing. This gets us to the end of talking about threads. We're going to use them throughout the rest of the semester on homework assignments, on exercises, and hopefully as a working software developer, you will use them a lot. I spent a little time at the start trying to convince you of what a thread was. And then to try to help with this, we looked at two APIs for making threads, one in C and one in Java. We talked a little bit about alternatives for how threads could be created within a process, either user threads that are made just in user space without necessarily any help from the OS versus kernel threads where the OS is independently scheduling all of our threads. And then we just did this. But we kind of talked about how as threading was introduced, and this was kind of when I was an undergraduate in computer science, so these have been around for a while. But as threading was introduced, it kind of forced us to rethink some existing mechanisms for threading. Before we move on to our next chapter, so our next chapter is on CPU scheduling. We're going to spend some time on that today. But before we move on, are there any questions about what we've covered so far? I'm hearing silence. I see people. So hopefully that means everybody feels pretty good about what they've seen so far. So I will switch to our next batch of lecture material. All right. So chapter 5 of your textbook is about CPU scheduling. And this is really about managing the ready queue. We talked about how the CPU has lots of queues of processes, lots of queues of process control blocks, where each queue kind of represents something that one or more processes may be waiting on. For each of those queues, there's going to be some kind of scheduler. It may be simple. It may just do them in queue order. But one of the most important queues is the ready queue. And the CPU scheduler is the one who decides how to manage that ready queue. It's sometimes called the short-term scheduler, or again, the CPU scheduler. Its job is whenever a CPU or a CPU core becomes idle, it's going to look at the ready queue and decide who gets to go next. It could just pick the first process on the queue. We could manage this queue in queue order, but one thing we'll talk about in this chapter is why you might want to do something more clever than that. In managing the ready queue, you might want to worry about, I've listed this at the bottom of this slide, you might want to try to keep the CPU as busy as possible or other devices as busy as possible. You might want to worry about fairness. You might want to worry about making sure everyone gets an equal share of CPU time. If you've got interactive users, like if you've got a user that clicked on the mouse, you might want to give them extra attention to make sure whatever process was waiting on that mouse click, it gets to run maybe before other processes. I've got prevent nuclear meltdown there. And what I really mean is you may have a system that has real-time processes where when something happens, like the user clicks a mouse or the temperature of something starts getting too high, maybe it is really, really important. Or, sorry, maybe it's driving a robot in the real world. And when something of interest happens, maybe it's really, really important that the process that's watching that gets to run soon. So maybe it gets to go to the front of the line, and other processes that have more elastic correctness constraints, maybe it's okay for them to wait. So these are all reasons we may not want to schedule the CPU in plain old first in, first out order. We already said all processes exhibit a CPU I/O burst cycle. That is, they want to run on the CPU for a little while, and then typically they have to wait for I/O. They want to read the next little bit from a file, or they want the user to type something on the keyboard. That's an I/O burst, so they wait for that, and then once they have that thing, they want to run on the CPU for a while, and then once they've done whatever they need in response for that, they have to wait for I/O. So like the picture over on the right-hand side of the slide shows, typically they just go back and forth between, I want to run, I need to wait for something. I want to run, I need to wait for something. The CPU scheduler decides who gets to run next. If there are multiple processes that all want to execute on the CPU, it decides who gets to go first. As we're thinking about what the CPU scheduler should do, or what would make sense, this picture shows something we will keep in mind. This is not true for all systems, but what this graph tries to show is the idea that most CPU bursts are short. Most processes, when they want to run in practice, they just want to run for a moment. And then they need to wait for something. Like if you had a program that was doing a graphical user interface. If you click a button, it needs to update the graphical user interface and then wait for you to move the mouse or press a key. That's a short CPU burst. It just needs to run for a moment. There are some programs that have long CPU bursts, but those are less common. And that's, again, this is, I think, a made up graph, but that's what this tries to show. If the horizontal axis, if the x-axis is how long is your burst, and the vertical axis is how common is that, then it's really common for processes to have short CPU bursts. It is much less common for processes to have long CPU bursts. And this isn't always true, but on a typical system, especially with interactive users, this is pretty common. So we'll keep that in mind because it might help us decide how we should manage the CPU or how the CPU scheduler should manage the CPU. I think I've covered some of this. The job of the CPU scheduler is to pick a process from the ready queue and give it a chance to run on the CPU. When does the CPU scheduler get run? So when does it get to choose a process to run next? I listed here the 5 reasons I could think of, or the 5 situations when the CPU scheduler might get a chance to run. The first one is maybe the most obvious. If you had a process that was running and it exited, well, it's gone, so I need to pick someone else to get a chance to run. When it terminates, it has to make a system call to the OS to say, I don't want to run anymore. So we've got to pick another system, or sorry, going to pick another process or thread to give a chance to run. That happens, but I labeled that as relatively infrequent because processes may run for, minutes before they decide to terminate. So this happens, but comparatively rarely. More typically, I'm going to bump ahead to a process blocks. This is probably the most common situation where the CPU scheduler gets to run. When a process is running and it decides it needs to wait for some I/O, it makes a system call saying, I want to read from this file. And then if it's reading from a file, that could take who knows how long. If it's reading the next key pressed by the user, that could take minutes, depending upon how fast the user is. So whenever this happens, whenever a running process blocks, the CPU scheduler has to pick another process to run on the CPU if we're trying to keep the CPU busy. So this is really frequent compared to a process terminating. This middle one, well, depending upon how you wrote your code, you may voluntarily yield the CPU. There's a system call for this. I think it's I think on Unix machines it's shed yield, S-C-H-E-D yield, but I may be wrong on that. But there is a call you can make to say, you know, I still want to run, but if someone else wants to run, give them a chance. Why don't you put me back in the ready queue and give me a chance later? And again, how common that is depends kind of on what OS you're using and how the user wrote the process. These top three are all, well, I'll sneak down to the bottom of my slide and I'll say they're all non-preemptive scheduling. The CPU scheduler picked another process to run because the currently running process either couldn't be run anymore, or it said, why don't you give someone else a chance? These next two, the one I colored in red, those are both preemptive executions of the scheduler. And all that means is I had a process that was running, it wanted to keep running, but I let another process have a chance. Schedulers that only run in these first three situations, we would call them non-preemptive schedulers. If a process is running, they let it keep running until I can't run it anymore, even if temporarily I can't run it anymore. A scheduler that will also run in these next two situations, we call that a preemptive scheduler. I've got a process, it was perfectly runnable, but I decided to give someone else a chance to run. What are these two situations? Well, I'll do the bottom one first. Maybe we talked about the timer interrupt in our first week of class. That was for CPU protection, so that even if a process wanted to run and run and run and run, occasionally this timer interrupt would go off, and that would give the OS a chance to let someone else have a turn. So if a process has had enough CPU time for now because the timer interrupt went off, the OS might let another process have a turn, and that would be a preemptive scheduling decision. The other one is, well, what if a process was runnable, but there was another, maybe more important process that was waiting on I/O? Maybe it was waiting on the user to click the mouse or waiting on the temperature of a nuclear reactor to change. When that happens, the CPU is going to get interrupted, and the OS also gets a chance to decide to let another process have a chance to run. In that situation, I labeled it as hardware interrupt here because maybe I had a process that was running, but something else happened on the system. The OS could decide to let a process that was waiting on that something else go ahead and run on the CPU, and that would also be a preemptive scheduling decision. If I had a runnable process that was running, but another process, the thing it was waiting for happened, I might choose to let it go ahead and execute. Probably spent too much time on this slide. Any questions before we move on? So I'm trying to define situations where the CPU scheduler might get a chance to run, and I'm trying to sneak in the definition of a preemptive versus a non-preemptive scheduler. Even after the scheduler has picked a job to run, there's still some overhead associated with switching to that job and letting it run. And that's called dispatch latency once you've chosen a job to run, or at least who gets to run next. It may take some time to let that process start executing. Again, that time is dispatch latency. And the dispatcher is the part of the OS that does that sets up some other process to run. And we already know some of what the dispatcher has to do, like I've listed here. If you pick a new process to run, I have to save the state of the old process. Typically, I have to save its CPU registers. I have to plug in the state of the new process, all of its CPU registers. I have to, including its memory bounds. I have to switch to user mode and then resume executing wherever that other process, wherever that new process was. And that's all the job of the dispatcher. We're about to talk about some particular scheduling policies you could have. We're going to have some criteria. We're going to have 5 official criteria for whether our scheduler is doing a good job or not. These are kind of like we talked about earlier in the scheduling chapter. These are things you might care about if you're worrying about scheduling the CPU. I've listed them here. I'll go through the names and some definitions for them. You might care about CPU utilization, which is, if your CPU was expensive and you had a lot of jobs to run, maybe you just want to keep it as busy as possible. So this is how often the CPU is busy. You might worry about throughput. As far as users are concerned, you just want to get their jobs done. Throughput is how many jobs you can complete per minute, say, or per whatever unit of time. A job typically consists of a whole bunch of CPU bursts. So we could kind of measure this at 2 levels. We could say, how long does it take for a whole job to finish? It's going to be hard for us to do that if a job has 1,000 or 1,000,000 CPU bursts. So often, if we're looking at what a scheduler might do, we'll look at this at a much smaller scale. We could define throughput as how many bursts do you get to complete per unit of time. So throughput could be measured in whole processes running and then completing, or typically we'll measure it just in bursts running and completing. I might marked those first 2 in blue because you generally want those to be high values. You want CPU utilization and throughput to be as high as possible. It's probably obvious, but the next 3 you want to be as low as possible. They're still criteria. It's just for things like turnaround time. You'd like that to be as short as possible. Turnaround time, just like throughput, we could measure that as a whole job. From the time I start a program, how long does it take until it's done? Well, again, that could be hard for us to look at for a particular CPU scheduler. So we will often look at this at a much smaller scale. For looking at what the scheduler does, we could measure this turnaround time as from the time a process enters the ready queue, how long does it take to finish its next burst? To get, if it wants to run, how long does it take until it gets to finish running that next burst? Waiting time is how much time does a process spend when it wants to run, but it's not running yet. Maybe some other processes are running. So waiting time is really how much time a process spends in the ready state. How much time does it spend when it wants to run, but it hasn't had its turn to run yet. Our last one, response time, this one's a little bit softer in terms of definition, but this makes a lot of sense for interactive applications. Response time says from the time when a process wants to run, when it enters the ready queue, how long does it take before it gets to start producing output? I say this makes a lot of sense for interactive jobs because if you got a user looking at the output from their process, and output could just mean painting a graphical user interface. How long does it take before they see some results from the actions they made? Usually for this, I say, if there's a button on the user interface and I click on that button, I would really like to see that button show that I've clicked on it. If it's graphical, maybe it shows itself in some pressed on state temporarily when I click on it. That's what this is trying to get at. Maybe a process doesn't need to finish everything it wants to do, but for interactive processes, if they get some input from a user, they're going to go into the ready state. How long does it take before they get to start producing output? How long does it take before they get to show that whatever the user did, like click on a button, to show that the program at least saw that happen? These criteria, so again, these are our 5 official criteria for measuring how effective a CPU scheduler is, depending upon what system we've got. We may care about one of these more than others. In the early days of computing, CPU utilization was probably really, really important. And nowadays, it's probably less important. CPUs are less expensive, so we don't worry as much about keeping them as busy as possible. We can't have all of these at once. Depending upon our system, we may care about one of these criteria a lot more than others. And trying to score really well on one criteria might cost you on another. For instance, if you care a lot about response time, that means whenever a new job enters, whenever a new process or thread enters the ready queue, you want to give it a chance to run as soon as possible so it can start producing at least some output. But if you do that, that means you're going to be doing more context switching. You're going to switch to processes just because you want to give them a chance to run early. And if you're doing more context switching, you're going to have increased overhead, which means your throughput is going to go down. You're going to have more wasted CPU time. And I kind of said this already, the right way to schedule your system depends on what kind of jobs it's running. If you've got interactive users, there may be things that you're concerned about that you wouldn't be if you're a batch system. If they just loaded you up with a bunch of jobs and you had to get them all done as quickly as possible. If you have real time, we'll talk about this later, but when I said maybe you're driving a robot or maybe you're monitoring the temperature of a nuclear reactor, I was really talking about real-time systems there where the timing of the execution of a program matters. It doesn't help to have a program to drive your robot that gets run after your robot has already fallen over. So some systems, the amount of real clock time matters in the correctness of that. This just means that the right way to schedule a system is going to depend on the system. It's going to depend on the kinds of jobs it's running. So we're going to talk about ingredients of a CPU scheduler. What things might we want to do? How could we build a CPU scheduler? And then kind of the idea is, at the end of this, realistic CPU schedulers are going to use a combination of these ideas. So we're going to start with the simplest idea possible, I think, for scheduling a CPU, and that's first come, first served, FCFS scheduling. This just says you're going to manage the ready queue in queue order. You're going to take whatever process is at the front of the ready queue and you're going to let it run, and then once it has finished running, probably because it made a blocking system call, probably because it had to wait for some IO, then you're going to give the next process a chance to run. So this picture up here at the top, or this little table, I'm pretending we have 3 processes, P1, P2, and P3. And so that we can talk about how they're scheduled, I've pretended they each have a particular burst time. P1 needs to run for 18 milliseconds, and then it has to wait for something. P2, we're pretending runs for 7 milliseconds. P3 needs to run for 3 milliseconds. So those are the times of their next CPU bursts. First come, first served is just going to schedule them in the time that they arrive, or sorry, in their order in the ready queue. It's going to schedule them based on their arrival time. So if this is the order that they're queued up, I'm going to run P1 first. And sorry, I started to say, we're going to draw these schedules as a Gantt chart. That is, if you were running a project and you're planning out what's going to happen, you might draw a chart like this to kind of show the order of tasks. A typical Gantt chart is more complicated than the ones we're going to draw because you might be doing multiple tasks concurrently. Here, we're going to pretend we just have one CPU. So our Gantt, or one core, so our Gantt charts are going to be really simple. This one shows if these 3 processes arrived in this order and we ran them in that order, then P1 gets to run first. It starts at, we'll say time 0 is when we start running these processes. It needs 8 milliseconds of CPU time, so it will run until time 18, and then typically it might have to wait for some IO, so the CPU scheduler has to pick someone else to run. P2 is next in line. It needs 7 milliseconds of CPU time, so that gets us up to time 25. And then maybe it makes a blocking system call or terminates. And then next in line is P3. It only needs 3 milliseconds of CPU time, so we're going to let it run up till time 28. And then we've, unless anyone else arrives at that point, we've drained the ready queue. There's no other process to run. So this is a Gantt chart that shows how these 3 processes would be scheduled in first come, first served order. Questions before I start trying to talk about this? There's still people here, so I'll assume that there are no questions. All right, what do I like about first come, first served? The main thing I like about it is it's really fast. And by fast, I mean it's really easy to pick the next job to run. The scheduler has very little overhead. It just gets the process from the front of the ready queue. If we implemented the ready queue as a linked list, we could choose a process to run in constant time, and as processes arrive in the ready queue, we could put them in the queue in constant time. It's just a few pointer manipulations. We said schedulers could be preemptive or non-preemptive. For this one, I think it has to be non-preemptive. I don't think it makes sense to have, I don't know what it would mean to have a first come, first served scheduler that was preemptive, because if a process is running, it got there first, so it gets to keep running even if new processes arrive. Is it any good? We said 5 criteria for evaluating a scheduler, and one of them was turnaround time. From the time when a process enters the ready queue, how long does it take for it to finish its next CPU burst? And for this particular case, we can figure that out. It's pretty easy. Here, I mean, if you back up, I didn't really show it, but let's pretend these 3 processes all got there at about the same time. Or I guess to make my life simple, I'm saying pretend we don't have to worry about when they arrive. They all pretty much arrived at time 0. Maybe P1 got there a little bit earlier and P3 got there a little bit later. So what's their turnaround time? Well, P1 got there at time 0 and it finished at time 18, so its turnaround time is 18 milliseconds. P2, well, we're pretending it also got there at about time 0, but it had to wait a while before it got to run. It finished its next burst at time 25. P3, well, it got there last, so it finished its burst at time 18. So for turnaround time, we can, here it is for individual processes. If we wanted to know how the scheduler is doing on average, we could compute average turnaround time. I just added up these 3 times and divided by 3 to get an average turnaround time of 23.67. So we can compute turnaround time, and it's easy if you've got a Gantt chart for a scheduler, it's easy to figure that out. But turnaround time might not be the best measurement. We've defined it, we can compute it, but some of this is not the scheduler's fault. Let's say this 25 here for P2. Well, of that, 7 milliseconds was time that P2 was running. And the scheduler, that's not really something it gets to choose. P2 just wants to run for 7 milliseconds, let's say. And turnaround time includes both how long P2 was waiting to get a chance to run and how long it actually ran. So maybe a better comparison between schedulers would be waiting time. That's how long they spent in the ready queue waiting for a chance to execute. And we can measure that also. For this schedule, Well, P1 arrived at time 0 and it got to start executing right when it arrived. So its waiting time was 0. The next one, P2, arrived at time 0, but maybe it got there a little bit behind P1. So it didn't get to start running until time 18. So its waiting time was all the way up to time 18. And P3 didn't get to start running until time 25. So its waiting time is this whole first 25 milliseconds when it was waiting in the ready queue. This is waiting time for individual processes. If we want an overall waiting time, we could add those together and divide by the number of processes, and that gives us a waiting time of 14.33 milliseconds. It looks like in terms of time, I'm about out of time, so I'll set us up for the next slide. Looking at this is kind of a deliberately bad schedule. Here, it seems like waiting time depends on scheduling choices, and here, it depends on the arrival order of these processes. If we got lucky and they arrived in the opposite order, well, we'll talk about this next time, but that would have given us a much better waiting time. We'll go through that next time. Let's call it a day for now. I'll hang around if you have any questions, but while I'm taking questions, I'll stop the recording and stop the screen sharing. Thanks for your attention. Good luck on the exercises this weekend. I'll see you next Monday.